Hello folks. Well, this time we want to start taking a look at implementation issues for object-oriented features in different languages, well, specifically in C++. So last time around we took a look at what kind of features we might want to include. We talked a little bit about inheritance and dynamic binding. So this time around I want to take a look at how you might actually make that work. Right? Let's face it, eventually, the compiler is going to turn all of this stuff into assembly language. So all of those weird and wonderful things that we're doing at the high level have to work at the assembly language level. So that's what I want to take a look at today, is how we can make some of this stuff work. So we'll take a look at just at a very basic level how we get the fields and methods themselves stuck into data someplace where they exist in memory, how they're organized. We'll take a look at inheritance and how that can work. We'll take a look at static dispatch, since that's the default for C++, where if you call a method, then by default the compiler is going to go through at compile time and figure out which one is supposed to be called. And then we'll take a look at how it manages to get dynamic dispatch working, so how it can get dynamic binding of methods to calls taking place. So these are the things that we want to take a look at for the next few minutes here. So the basic idea is that all of this stuff was originally for C++ built off of what was available in C. So the original implementations of C++, it was actually programmed in C. And so if you had something like classes, it was pretty natural to turn around and use a struct-like approach for holding the data fields. Right? So it makes perfect sense that the data fields in your class are just represented the same way as they would be in a struct. So you've just got a whole bunch of fields stored in a row in memory, possibly with some padding in between to support your memory alignment and whatnot. And then since we've got function pointers available to us in C, then the idea was, okay, well, for methods, all we have to do is stick a function pointer inside the struct. So when you call a method on an instance of a class, then what it actually does is look at the function pointer, call the function pointer, and pass it also the address of the specific struct it's supposed to be working on, right? The one that's got the data in it. So this is the essential idea for how this stuff is going to be organized. And then when it comes to inheritance, we'll start looking at saying, okay, well, if I've got this kind of a notion for how the structs are laid out originally, what do I have to add to them to get inheritance going on? The static dispatch is pretty much what we're considering here in terms of how we handle our method calls. And then we'll get into how we can add additional data types to this kind of a thing so that we can make dynamic binding, dynamic dispatch work. So we'll just run through each of those in sequence. So again, the notion is that as far as storage goes, we'll just store the fields based on a good old-fashioned C-style struct. Now, the modern implementations of C++ clean this up a lot and come up with a more efficient approach to things, but the underlying idea still gives you a pretty good feel for how things can be handled. Again, the methods will simply have, within our struct, we'll have function pointers, and then the actual code for the method that we want to run is going to be implemented someplace else as just a regular old global function. But since that means that, if I've got 60 different classes, maybe they've each got a print method inside them, and they're each represented as calls to global functions someplace, then all those functions need to be uniquely named. So they have to have some way of saying, oh, this is the print for my circle class, and this is the print for my window class, and whatever else it might be. So this is where the syntax comes from, this notation where we refer to things as the class name and the 2 colons and then the method name. So somewhere out there, if I've got a method called a method in my class, then there's actually a function lying out there someplace called some class : a method, and this is the way the compiler's thinking of things. Now, that does mean that when that function gets called, it has to know which instance of some class, which specific instance of the struct has the data that this call is supposed to operate on. So that's where the notion of the this pointer comes from. Behind the scenes, hidden to the developer, when the compiler goes off to create this function, it inserts an extra parameter at the front of the list that's a pointer to the struct that you're calling this on. So a pointer to my some class struct, if you want to think of it that way. And that's where the notion of the this pointer comes in. So I'm going to take a look at this from the point of view of what the developer sees and then what might be happening under the hood. And again, it's not going to be this simple in modern versions of C++, but this gives you a basic idea of how this can be done. So let's say we've got our class. It's got a data field in it. I'm just going to leave everything public for the moment. So we've got a data field I, and then we've got some function, or some method rather, foo, that takes a parameter and, okay, slide glitch. So this is supposed to be returning x plus I. So this method would be returning its parameter x and the field, whatever the value of the field I was in here. So picture, if you will, that return statement is actually in here. And then, so we've got our class, we've got a method inside it. Somewhere off in our program, we create an instance of that class. So I've got my variable a that's one of these classes. And then inside it, I call, or somewhere further on in the program, I call the method foo on a and pass whatever the parameter value happens to be. I pass a 3. And it's supposed to go off and take whatever the value of I is, add 3, and return it. Right, so this is what the developer sees, nice and clean. Behind the scenes, again, the compiler is turning this into, okay, well, we're going to have essentially a glorified struct that's got this integer field in it, and then it's got a function pointer for the method. And so we've got, this thing's going to return an int like it's supposed to. It's going to take an int as a parameter. It's a function pointer. And it's going to take one extra parameter that the compiler's inserting here that's a pointer to the instance of the struct that we're actually going to work on. So it's taking a pointer to a C as a first parameter. And then the method, when it goes to implement it, it's going to say, okay, well, I've got to return an int. I'm going to give this thing a unique name. So it's going to be my C : foo, right? The class name, method name. The first thing it's going to take as a parameter is a pointer to whatever data it's supposed to be working on, whatever actual struct it's supposed to be working on, and then whatever parameters the developer said to pass. And then inside, I'm going to say, okay, return the parameter x plus, and then I need to look up the value of I within that particular instance of the struct. So the compiler is doing this for you, so you wind up getting behavior like this. Now, that means that in the actual call, where you say result is equal to, a.foo, it's got to say, okay, well, a is my struct. I've got to look up the function pointer inside it. I've got to call that function through the pointer. I have to pass the address of the struct that I want to work on and whatever the other parameters are. So again, the compiler is doing this behind the scenes so that you get to see some nice clean syntax, but this all still actually works. So you can get a reasonable class-like behavior with a relatively simple transformation. I mean, the syntax is ugly from a human readability point of view, but the transformation itself is not that difficult. So let's move on and consider inheritance next. So now we're saying we've got, a parent class that's got a couple of fields in it and a child class. Maybe the child class overrides one of those parent class fields and adds a new one of its own. So what we really want is for the child class to have, theoretically, the x that it inherited from the parent, somehow the y that it inherited from the parent, and its own y as well, so it can use either one as needed, and then the new z field that it's adding. So what the compiler is going to do is just say, okay, well, when I create an instance of this, I'll essentially create, this. I'm going to put this in the sort of struct notation we would think of, but of course the compiler is just thinking of this as a bunch of memory with a bunch of offsets to it. But it's going to think of this as, okay, well, I've got space for the parent x, I've got space for the parent y, I've got space for the child x, and I've got space for the child z. Right? So we're just saying, okay, for each one of these things, we'll have a unique one inside the more complex child class structure. And then it would be the same idea for methods, right? If I had a method foo in the parent and I overrode that with a method foo in the child, we'd have a function pointer in here for the parent version and a function pointer in here for the child version. So again, the basics of inheritance are also pretty straightforward. Syntax would be ugly if we had to do it manually, but it's all workable. Where life gets challenging is where we decide we want to start doing dynamic dispatch. Right? By default, C++ uses static dispatch, so when you call a method on a variable, it's just going to look at that and say, okay, well, what's the data type for the variable? I'm going to use that type of method, and it's just going to do that at compile time. So if we think back to something like our a.foo here, it's just going to say, oh, well, this is an instance of C. I'll call the C version of foo here. Right, so if we've got whatever we see as the data type at compile time is the data type that we'll, or the type that we'll use for the method. So static binding by default. If I want to tweak that and get it to work with dynamic binding, dynamic dispatch, then I need all kinds of things. I need a way for the developer to say, I don't want you to use static binding on this. I want you to use dynamic dispatch on this particular method. So we need a syntax for doing that first, and then we need a way for making it actually work during execution. So the syntax in C++, and I'm sure you've all played with this now, you've all seen this by now, where we go through and create an abstract base class, and we've got a pure virtual method where somewhere in that abstract base class we see something like this. We've got a virtual void method, or well, whatever the return type might be, and we actually set our function to 0, which always looks really weird the first time you see this kind of syntax in C++, because you're saying, well, what am I doing setting a function to 0? But now that we know that the way this is getting implemented is that foo is just a function pointer, then what this is doing is saying, okay, I'm just going to set that pointer to null. And so that's the way C++ has of saying, okay, there isn't actually an implementation for this. We're sticking in a null pointer there, and that's what enables it to say, okay, if you want to actually create a callable instance of this, then you're going to have to override foo in every class that's derived from your base class. So every class that's derived from this has to give an actual implementation for the foo method in that derived class. Right? Otherwise, we just have a null pointer there, and we can't actually call a foo. So it gives the compiler a way of recognizing that, foo is a null pointer. It doesn't point anywhere. This has got to be something that's figured out dynamically. And it gives you this forced notion that you have to provide real versions later when you actually implement the base classes, or the derived classes, rather. So the other half to that is when you actually make a call to foo somewhere in the program, the compiler has to have code inserted at that point so that it stops or pauses then and figures out, gee, what class instance am I dealing with, and therefore which version of foo am I supposed to call, and how do I find that right version? So the way this is going to work is that for each class, the compiler is going to create a virtual function table. You'll see this called vtables. So this is just a lookup table that's got a bunch of function pointers in it. And so what this is going to contain is pointers to each of the locally defined methods, that class defines. So if I've got a foo defined in my child class, it's going to have a pointer to that foo. So we'll have all these pointers to the local versions of the methods, and then we'll also have pointers to each of the ancestors' vtables. So if I have my child class, it's got pointers to its own functions, its own methods, and it's got pointers to the parent class vtables, which contain, of course, the pointers to the parent methods. So what's going to happen is when you hit the actual method call, this inserted code that the compiler put in to start this lookup process is going to say, okay, I'm going to look at my local vtable and see if I've got that method locally. If not, then I'll go off and look at my parents table and see if it's got it. And if not, it'll have a pointer to its parents table, and I'll go off and look at that one. And so we can find our way back up the chain to the function table that's got the pointer to the right method for us to call. And so we can effectively get the most localized, most specialized version of the method and invoke that. So it does mean that if you're using dynamic binding in something like C++, if you're using dynamic dispatch, that there is a little bit more taking place when you make a method call, right? Because when you make that method call, it's going through at least the one lookup table to figure out which method it needs to call, and possibly it's going through more lookup tables. So you can get all this to work. I have not posted a link for some good sample code for this, but I will try and remember to do that. But again, it gives you an idea of how you can go through and actually implement something like this, how you can get it to work at runtime. And if you ever find yourself in a situation where this is the kind of thing that you want to do in a language that doesn't directly support it, if you find yourself in the unfortunate situation of you're playing with a language like C and you want this kind of behavior, you can do it. Right? I mean, obviously it's been done before. C++ was originally implemented in C. It's all possible, and this is one approach to doing it. All right, we will leave it there and move on to our next topic.